So now that we've defined some trig functions like sine, cosine, etc., the next question would be, well, what if we were to graph the inputs versus the outputs for some of those? Okay, so that's what 5.3 is looking at. Actually, 5.3 and 5.4 are both looking at trigonometric graphs. So starting out, the question is, could I come up with graphs of, say, cosine of x and sine of x? So I just set up a little table of values here. Now what I did for my inputs, my independent variable x here, I just chose multiples of pi halves, because those are going to give me really nice numbers to work with as far as outputs for sine and cosine. Now I could always go back and add values if I don't have enough information to come up with a graph, but let's see if I do. So let me start with, say, cosine. Let's start with 0. Okay, cosine of 0. So cosine is the x coordinate. That would be 1. Cosine of pi halves. That's the x coordinate. That's 0. Cosine of pi, x coordinate is -1. Okay, cosine 3 pi halves, x coordinate is 0 again. 2 pi, I'm back over here, so you see the pattern. Let's see, negative pi over 2 is here. Negative pi is here. 1, 2, negative 3 pi over 2 is here. 1, 2, 3, 4, negative 2 pi. I'm back where I started. So let me see if I can plot those points. So I set up a plane here, scaling in terms of pi halves on the x-axis, integers on the y-axis. Let me plot these points. So I have, let's see, negative 2 pi, comma 1, negative 3 pi over 2, 0, negative pi, negative 1, negative pi over 2, 0, 0, 1, pi halves, 0, pi, negative 1, 3 pi over 2, 0, 2 pi, 1. And so what I have here, try to do a decent job drawing it if I can. I have a wave. Okay, so this is my cosine wave. Try to make this look like a nice, smooth, continuous curve. Okay, now that would continue following that same pattern. Let's look at a couple of features. So this is the graph of cosine of x. Just curious if it'll let me do that. I don't think so. Okay. Anyway, let's see. So what can I come up with for cosine? Well, the domain, the set of inputs, that's all real numbers, right? I can extend this all the way across. The range, let's see, the lowest value of y is -1, the highest is 1. So the range would be -1 to 1, including the ends. What else can I come up with? Something called the amplitude. So this is, so maybe I'll write something. So from the center of the wave, this is the distance to, you could say to the top or to the bottom. So since it's a distance, this is always positive. Okay, so I start at the center of the wave, and then I measure what is the distance to either the top or the bottom. Either way I look, that distance is 1, right? So my amplitude is 1, and that's always a positive number. Something else I could come up with, the period. So what I'm interested in when I'm asking for the period is, like, you see how this graph is repetitive, right? I mean, I really have the same shape over and over and over again. So the question with period is, well, how much of the graph, like what length would I have to cut out so that I could then just tack that on again and again, and I'd really have a complete graph? So there are different ways I could measure that. If I started like here at 0, okay, the next peak is here, right? So if I was to cut this distance, this period of 2 pi, I could actually just take that chunk and tack it on again and again, and then I would have the complete graph all the way across the x-axis. Now, I could measure, you know, from something else, pick a different color. Like if I picked this valley, say, then to the next valley, I should have that same period. Pi plus pi, you can see the period is again 2 pi. So no matter how I look at it, the period is 2 pi. Graph for sine of x. Okay, so I haven't done that yet. So let me go back up here to the table and start at 0. What is sine of 0? So now I'm looking at each point, I'm looking at the y value. Sine of 0 is 0. Sine of pi halves is 1. Sine of pi, 0. Sine 3 pi halves, negative 1. 2 pi back at 0. If I go in the negative direction, negative 1. Let's see, 0, 1, and 0. Looks like I have a pattern again. So let me plot these points. Negative 2 pi 0, negative 3 pi halves 1, negative pi 0, negative pi halves negative 1, 0, 0, pi halves 1, pi 0, 3 pi halves negative 1, and 2 pi 0. So here's my sine wave. So you'll notice this looks really similar to the cosine wave, just shifted. There's my graph of sine x. So look, the domain is the same, the range is the same. Let's see, from the center of the wave, that distance is still 1, the amplitude's the same. What about the period? Well, look. So the period, looking at my sine graph, let's see. A couple different ways to measure. Okay, if I start here at the origin, I'm saying here I'm coming up. The next place on that graph I'm coming up is here. So I could measure the period that way. That distance is 2 pi. Or I could say, okay, here's a valley. My next valley is here. 3/2 plus 1/2 is 4/2. So the period is also 2 pi. Okay, so there are my sine and cosine graphs. And those were not too hard to come up with. Those basic graphs of sine and cosine look like, we can actually do some transformations problems. So these are like the same as before. So the first thing I have to do is identify what is the base graph. Okay, so that would be cosine of x. So that'd be my first step. Now I kind of remember what that looks like, but I mean I can quickly plug values in. So let me see here. Cosine of 0, that's 1. Cosine of pi over 2, that's 0. Cosine of pi, negative 1. Cosine of negative pi over 2, 0. Cosine of negative pi, negative 1. And then I fill in that graph. Now, notice a couple of things. So really, I only need to show one full period, and the period is 2 pi, right? So I know after this, the graph just repeats, right? So this would be a sufficient graph because I've shown a full period. Now, notice my labeling. I need to make sure everything's very carefully labeled. So I have a couple options. I can do what I did here, and I can carefully label the scale here on the x-axis. Okay, now I can change the scale in, later graphs. It's just important that whatever I choose, like, I don't know, say this one here is a fourth, just for fun. Then this one, since it's twice as many blocks, it would have to be twice that, right? So then I'd be going in fourths, you know what I mean? I can scale this however I want. It's just that, let me show you like what I don't want to do is say like, this one's a fourth, and then I'm just going to say this one's a third, and then this one's 1. I can't do that. Doesn't make any sense, right? Because this one here is twice as many blocks as this one here. Okay, so one idea is just carefully labeling the x and y scale. That's what I like to do. The other option would be, I guess you could come in and you could clearly label each of these points. You know what I mean? You could do that. That's another idea. Either one. But everything needs to be clearly labeled so that we can see what corresponds with what and not just the correct shape. Okay, so I like labeling the axes, but let me look at the next step. So remember, when I'm doing transformations, I need to look for multiplications and divisions. So the multiplication that I see is this 1/2 inside the trig function. So remember that if this is inside, it's going to be affecting x. Now remember, x things happen opposite of how they look. So at first glance, that looks like I divide the x's by 2, so I would do the opposite. So actually what I have here is a horizontal stretch because the x is actually getting bigger. So all I need to do is take each point on the previous graph and I just follow this rule. Okay, so I mean, if I start with 0, 1, that's not going to go anywhere. So if I multiply 0 by 2, it's still 0. My next point, the one that's here at pi halves 0. So I'm going to take pi halves, multiply it by 2. It's going to be at pi 0 now. So what I would do in that case is I would actually change the scale and make that pi. Clean this up a little bit. The next point, at pi negative 1, I'm going to multiply the x by 2. It's going to be at 2 pi negative 1. Okay, so I'm carefully labeling my x and y scale. Let me look on the left side over here. So this negative pi halves, I'm going to multiply by 2. It'll be at negative pi. 0. And negative 2 pi negative 1. Okay, so then let me connect my dots. And so I have a horizontally stretched cosine wave. So that looks nice. My x and y scales are clearly labeled. So let me go to the next step. So the third step is going to be accounting for that pi over 4. Step 3 is graphing this guy. Okay, now be careful, because do you remember the problem like this? We did this problem like back in the section we looked at transformations or something similar. If we had something like this, remember this was not a shift right by 4. Remember what we had to do as the first step is we had to factor out the coefficient on the x. So remember, this was actually a shift right by 2. Okay, so this is very important. So the problem that I have at hand here is actually similar, because you see how I've already accounted for this 1/2? That affects x just like this does because it's inside. So what I have to do is I have to factor out the coefficient on x. I'm going to have to do that anytime there's a coefficient on the x value here. So means I need to factor the 1/2 out, figure out what's going to go here. So what times 1/2 is pi 4ths? Isn't it pi halves? Okay, so actually what I have here is a shift right by pi over 2. So don't forget to factor out that coefficient on x. Okay, that's very important. So now I'm just going to take my previous graph and I need to move everything right by pi halves. So I have to decide on a scale. I mean, this point here, it's going to move to pi halves. This one's going to move to 1.5 pi. So I think the appropriate scale would be pi halves. So let me go ahead and label my axes. So pi halves, pi, 3 pi halves, 2 pi, 5 pi halves. Phew. Excuse me. Okay, and let's go ahead and make the graph. So should I start over here? So 2 pi, that's 4 halves. So I'll move that right by a half pi. So now it's going to be at 5 pi halves, -1. Pi 0, that's 2 halves. So that'll be at 3 halves pi, 0. 0, 1 is going to be at pi halves 1. Negative pi is going to be at negative pi over 2. And negative 2 pi, that's negative 4 halves, that'll be at negative 3 pi halves. Okay, let me connect the dots. Use the blue marker to try to make that look like a smooth, rounded, continuous curve. And so there's my final graph of that trig function. Let me fill in a few things. The domain for sine and cosine is easy. The range, I just have to look at the y values on the graph. So the lowest is -1, the highest is 1. So that hasn't changed. The amplitude from the center of the wave, the distance to the top or bottom is 1. So that hasn't changed. What about the period? So that's asking how much of the graph would I have to show so that I really have a complete graph, because after that I have a repetition. So there are different ways of counting. Let me see. Let me count from valley to valley. So look, here's a valley. The next valley is over here. So what is that distance? I have 5 halves plus another 3 halves. I have a total of 8 halves. So that period is actually 4 pi. So that's kind of interesting, but it makes sense because you see how in this step I affected the x. I stretched the x's by 2, right? So the period is a horizontal measure. So what I did is I took the period of 2 pi and I multiplied it by 2. So it's now 4 pi. Just clean this up. There's one more term I didn't mention yet. It's called the phase shift. So this is a shift left or right. Okay, so this problem, let's see what we did. We shifted right by pi over 2. So we would say the phase shift is pi over 2, positive pi over 2. If it were shifted left, we would indicate that with a negative. We would say the phase shift is negative pi over 2. shall we try another one? So with number 2, you can see the base graph would be sine of x. So let's see, sine of 0 is 0. Sine, let's see, should I do sine of pi halves is 1. Sine of pi is 0. Sine negative pi halves is negative 1. Sine negative pi is 0. It's going to look something like that. There's my base graph. I have a full period. Now I'll look for multiplication. So this time I see a few. So I can do these multiplications in any order. Actually, I guess I'm going to try to do 2 at once here. So you see how I'm affecting, both the negative and the 3 are affecting the sign. So what I'm doing there, remember why things happen directly. So I'm taking all the y's and I'm multiplying them all by negative 3. So if I make my y's negative, I'm reflecting over the x-axis. If I multiply my y's by 3, I have a vertical stretch. So I'm doing both of those things in one step. So let me look at my points. So pi 0. I'm going to multiply the y by negative 3. Okay, so that's not going to move. So that'll still be at pi 0. What about pi halves 1? So I'm going to multiply the y by negative 3. So pi halves 1 is going to go to pi halves negative 3. Okay, 0, 0. Again, if I multiply 0 by negative 3, it's still 0. Negative pi halves negative 1, I'm going to multiply the y by 3. By negative 3. Oops. So if I multiply negative 1 by negative 3, I actually get positive 3. Okay, negative pi 0, multiply 0 by negative 3, it doesn't move. I draw my graph. So I've reflected and I've stretched vertically. Just clean this up, make this look nice. Okie dokie, so what's next? So again, I'm looking for multiplications. Multiplications or division. So look back at my equation. And I can see the other multiplication here is by this 2 pi that's inside the parentheses. Okay, so because that's inside, I know that's affecting the x. So remember, x things happen opposite of how they look. So instead of multiplying the x's by 2 pi, we're actually going to be dividing the x's by 2 pi. So then I'll actually be making the x's smaller. This will be a horizontal compression. Okay, so I need to take each point on the previous graph. I'm gonna move this, I think. For now, okay. So if you look at the points on the previous graph here, this one, so I have this point at pi 0. So I'm going to divide the x by 2 pi. So now that point is at a half 0. Okay? The point here at pi halves, -3, going to divide the x by 2 pi. So let me do this off to the side. So pi halves divided by 2 pi. So I flip and multiply. It's 1/4, isn't it? Zero's not going to move. What about negative pi halves, +3? That's going to be similar to the last one that I did. If I take negative pi halves, divide it by 2 pi, it's going to be the same calculation up here, right? Except for a negative. So it's going to be -1/4. Then this last point here, so I divide negative pi by 2 pi. That'll be -1/2. 0. Okay. Something like that. And then what's the last step? This is a long one, huh? The last step is to account for that shift. So that's the case where, remember, I have to factor out that coefficient. Okay, so 2 pi times what makes pi? Is that a half? If I distribute that through, I would get pi, indeed. Okay, so actually what I have here is a shift left by a half. So I guess my scale can stay as it is. I might want to, let me do this. See if I can do this. Move this over. Because I'm gonna need more space on that side. Okay. So we'll go with 1/4, half, -1/4, -1/2, -3/4. Okay, so all my points here, I'm going to be moving them left by a half. So that point, oh, it's going to be, I should have moved that even further, shouldn't I? Well, because it's going to be starting here, maybe I'll be able to squeeze it in. So that point will be at 0, 0. What about this point? Point at a quarter, if I go left by a half, it'll be at negative a quarter. Negative 3. And then 0, 0 is going to be at negative a half, 0. And then negative a quarter, 3 is going to be at negative 3/4, 3. And the last one should be at negative 1, 0. Let me do that. Looks like it. That way I have room to extend this. There we go. All right. And so I finally have my final graph. Okay. Let's erase the scratch work and then let's fill in the domain, range, etc. Domain's the easy part. Range looks like negative 3 to 3. Amplitude, so from the center of the wave to the top or the bottom, that distance would be 3. So let me show you a trick for finding the period. So in general, we write this equation. The period is 2 pi divided by k, if we're interested in sine or cosine, because the period starts out as 2 pi. And then the k is whatever the multiplier, the coefficient is on the x here. So even if you look back at the original equation, you can read the k off. The k is 2 pi. So if I take 2 pi and divide it by 2 pi, the period is 1. Well, does that look correct? It does, because the distance from here to here is 1 unit. What about the phase shift? This guy was shifted left by a half. So we'd say the phase shift is negative half. Okay. So, I mean, I can actually read some information off from these just by kind of looking at them. So, like, let me just write something down here. Put it here so we have plenty of space. So say I just write an equation. Let's do a third. All right, let's do that. So I'm just curious, just by looking at the equation, can we tell the amplitude, the period, and even the phase shift. Okay, so actually the number here gives me the amplitude, right? Because that 4 is going to be a vertical stretch, so it's going to stretch that amplitude. So I could just use the number in front, but I have to take it in magnitude because the amplitude, remember, measures a distance. The period, I can use that 2 pi over k. The k is 1/3. Six pi. And then be careful to get the phase shift. I'm going to have to factor out this 1/3. Okay, what number times a third makes 1? Is it 3? Yes. So that's a shift right 3. So the phase shift would be positive 3. Okay, so I can actually read a lot of that information off without even graphing. So let me go back to this last example. Write the equation of each graph. Okay, so here's a number 1. So let's see, to me when I first look at this, I see that I have my peak on the y-axis. So to me this looks like a cosine of something. Okay, so what is the amplitude? The amplitude is 4, right? So that's what I was just talking about. I would have a 4 in front. Now, if I look at this graph, what is the period? The period looks like pi, okay? So remember, in general, I know the period is 2 pi divided by the k. So the k is what I need to solve for. So for this specific graph, I know the period is pi. So actually what I'm doing this time is I'm actually solving for k by using the period which is known. Okay, so that means here's my equation of that graph. Now that'd be the simplest way to write the equation, but I mean if I wanted to, I could write it as a sine graph. Would just have to be shifted. So let me see here. So if I were to extend this, it would come down through here, right? So if I want this to be a sine graph, well, the amplitude's the same. The period's the same. The only thing that's going to change, like I said, is I'm going to need a phase shift. So let's see. A sine graph starts out like this. So I would have to take that and shift it left by pi/4 to get the given graph. So wouldn't it look like so? Shift that graph left by pi/4. And I could even come up with more, but I'll stop with those two. So if I was just asked to come up with an equation, I would just go with this one. But if I needed another idea, there I have another idea. Okay, let me try this next graph. Okay, so to me, looking at this one, I see the graph goes through the origin. So my first thought is to write a sine. Okay, now I can see the amplitude is 1/4. So let me solve for k. And I can do that by using the fact that the period is equal to 2 pi over k. Okay, so what is the period? Period of this one is 6 pi. Okay, there's my equation. Or if I really want to write this as a cosine, let's see what that phase shift would have to be. Let's see, so a cosine graph looks like so. So I'd have to take that and shift it right by, what is that, 1.5 pi? So if I shift that right by 3 pi over 2, that'd be another